Hello everyone, this is going to be part 2 of the video solutions for the test 2 review questions, and we are going to start with this particular question on normal distribution and finding areas under the curve. All right, so let's read this. It's a pretty straightforward problem. It's not an application-based word problem, but let's read through it first and understand what we have to answer. It says here, variable is normally distributed with mean of 10 and standard deviation 3. Find the percentage of all possible values of the variable that lie between 6 and 7. All right, so I think this is a problem we had in one of our worksheets, but I'm going to just go over it again, since it's a part of the review questions. All right, so the mean here is 10. All right, so here it says a variable is normally distributed. Just a second, let me get out my pen out. It's normally distributed, and this phrase is very important because a variable must be normally distributed in order for us to use the normal distribution table. All right, and the mean mu is 10, and the standard deviation, and these are all population standard deviation and population mean, has a value of 3. Find the percentage of all possible values of the variable that lie between 6 and 7. So here they're asking for the percentage, but remember, percentage is converted from the area under a curve. All right, so percentage is a form that can be converted if we know the area under the curve between two z values. So let's go about the process. The first step is just draw a diagram. All right, if you have the diagram before you, then it should not be very difficult to follow the steps. So here we have the diagram, a normal curve. And in a normal curve, the mean is going to be at the center. All right, so here the mean is 10, so that's why I have a 10 here. And then the two other values of the variable are 6 and 7, and they want us to find the area between 6 and 7 essentially. All right, so in your diagram, mark where 6 and 7 would be relative to 10. So it would be 6 and 7 are both less than 10. So it should be located somewhere to the left of the mean of the center point. So I've denoted 6 here, and then 7 is greater than 6, so it should be to the right of 6. All right, and once I mark those locations on the horizontal line under the curve, just extend the two vertical lines from 6 and 7 and shade the area in between 6 and 7. So we are looking for the area, this particular shaded area shown in yellow highlight. That's the area, that's the region of interest for us. Now we cannot work with 6, 7 and 10 to find the areas. We have to use our z table, and before that, before we go to the z table, we must have our z values here. Negative 1.33 is the z value corresponding to 6. How did we find that? Using the formula. What is the formula for z? It's x minus mu over sigma. So here we are working with the population, all right, with the entire population. So it's going to be x minus mu over sigma. We are not talking about sample means, all right? If it was that, then we would have to use a slightly different formula for z. But here we are just working with the population, therefore a z value is going to be found using the formula x minus mu over sigma. So I first found the z value corresponding to 7. So 7 minus 10 divided by 3, it gives us negative 3 over 3, which is negative 1. And then I found the z value corresponding to 6, and plugging in the values, 6 minus 10 divided by 3 is negative 4 over 3, which is 1.33. Now, I just want to again stress that you must show all the steps to get the full points for a particular question. All right, if you skip steps, every step has points assigned to it. So if you skip the steps, then you will lose the points for that step. All right. And moreover, if your answer, for some reason, if the final calculation is incorrect and if you've not shown the steps, then you end up getting a 0 for the question. So it's very important that you show the steps. Now, so once we have our z values, negative 1 and 1.33, we have to go to our table to find the areas, all right, corresponding to each of these. Again, now you can go to the table and pull it up and find the areas I've shown a few times in the previous video, in the previous question. I have already showed once how to refer to the table to find the area, so I'm not bringing up the table again. All right, so the area to the left corresponding to negative 1 is 0.1587, and the corresponding area for 1.33, for a z value of 1.33, is 0.0918. So you have to subtract this these two numbers. So 0.0918 has to be subtracted from 0.1587 to find the area between the 2 points. All right, because 0.1587 is all of this area, all the area to the left of -1. All right, so we are not interested in this area here. We are not interested in this area, right? This has to be subtracted. How do we subtract that? We subtract the area to the left of negative 1.33, and that's why we need to do that subtraction. And the final answer is 0.0669. All right, when you do the subtraction, and the question asked us for percentage, so make sure you're answering the question accurately. If they've asked for percentage, then give the percentage form by converting 0.0669 to percentage. Multiply it by 100 and you will get the percentage of all possible values between 6 and 7 is 6.669%. If they ask you for probability, please give your answer in the form of decimals. Probability is not represented as percentage. All right, so be careful about that, otherwise you may lose some points. The next question says, are at least 10. All right, so again, draw a diagram. Start with a diagram. At least 10. Where is 10? 10 is also the mean, right? Now, what does at least mean? At least means that 10 is the lowest value. It could be everything higher than that, greater than that. So 10 and higher. So it essentially means greater or equal to 10. All right, so everything, greater means everything to the right of 10. Correct? So we have our 10, which is the mean. This is also the mean, so that's why it's at the center point. And because we use the phrase at least, that tells us it's everything greater or equal to 10. And therefore, our region of interest is everything to the right of the center point. All right? So what is the corresponding z value? Okay, so 10 minus 10, again, it's x minus mu over 3. Here, x and mu are the same value. They happen to be the same value, correct? That's why 10 minus 10 divided by 3 is 0. The area to the left of a z value of 0 is 0.5. How did I know that? I used the table. All right, I used the table, but I'm not referring to it. I'm not displaying it here. You should know by now how to refer to the table. Otherwise, just go over my previous videos to see how I've shown how to use the table. All right. So area, now we need the area to the right. The table gives us the area to the left only. All right, so this is area to the left. Our region of interest is area to the right. So how do you find area to the right? Very easy, 1 minus whatever the area is to the left. In this case, it's 0.5, so area to the right is 0.5. What does it mean in terms of percentage? It's the percentage of all possible values of at least 10 is 50%. 0.5 means 50%, correct? You just multiply 0.5 by 100 to get the percentage form, right? So that's B, and now we have part C. It says we have to find the percentage of values that are at most 17.5. Now, what does at most mean? At most means 17.5 is the upper end. It's the highest value. It can be less than 17.5, but it cannot go higher than 17.5, right? So at most means less or equal to 17.5. And whenever we have less than, that means our region of interest is left side area. Okay. So for these questions, you have to know what at least and at most translates to. At least means it's greater than a certain value. At most means it would be less or equal to a certain value. All right. So I've drawn always start with the diagram. I've drawn my diagram. 10 again is at the center. That's the mu. Mu is always at the center. And 17.5 is way to the right. It's greater than 10, so it should be placed way to the right of the mean. And then I've shaded the region to the left because our region of interest will be to the left. It's less or equal to 17.5. So now that we have our diagram and we know our region of interest, we have to find the corresponding z value before we can go to our table. So 17.5, which represents our x, minus mu, which is 10, divided by 3, which is the standard deviation, gives us a z value of 2.5. When we go to the table to find the area corresponding to 2.5, it's an area of 0.9938. All right, so now its area to the left is what we were looking for. The table directly gives us areas to the left, so we do not have to subtract from anything as we did when we wanted to find the area to the right or between two values. So this is this stops here. All right, you just have to convert 0.9938 to percentage form by multiplying by 100 the percentage of all possible values that are at most 17.5. Now let me correct this. Should be the values at most 17.5 is 99.38%. All right, 99.38%. Right? So let's go to the next one after this to see what questions we have in our review sheet. This completes all the questions pertaining to a normal distribution. Okay, now we will be answering questions on from chapter 10, all right, which is the sampling distribution of the sample means. The first question is, write the equation for each and say when the following should be used to determine a confidence interval. All right. Now, standardized version and the studentized version is what they're asking for. Now, Z equals X bar minus mu divided by sigma divided by square root over n is the formula for the standardized version. That means when we use the Z value, all right, and then the standardized version, when is it used? When the population standard deviation sigma is known. The studentized version is used when the population standard deviation is unknown. We use what's called a t-distribution, which is x bar minus mu divided by s over square root over n. When is the studentized version used? It's used when the population standard deviation is unknown and the sample standard deviation S is used. So when we do not have the population standard deviation given to us, we have no other means but to use the sample standard deviation in our calculation. And when that happens, we cannot use the Z value. We have to use what's called the T statistic, which has a slightly different formula from the Z. The only difference is instead of sigma, we have to use S in our calculation, and the T distribution is a separate distribution for or based on the sample size we are using. And that brings into play what's called the degrees of freedom, the DF. So whenever you are using the T value, you have to also refer to the DF, the degrees of freedom. All right, now let me just correct myself a little bit. Initially when I started on this explanation, I had perhaps mentioned that this is a question on chapter 10, the sampling distribution of the sample mean, but this is really on confidence intervals. We covered this when we were on the chapter of confidence intervals. All right, so if I misspoke, I'm sorry about that, but I stand corrected that this is a question actually from chapter 11, which is on confidence intervals. All right. Now, part B says, how does the sample size have an effect on the mean of all the sample means? Now, the sample size has no effect on the mean of all the sample means. Mu sub x bar equals mu irrespective of sample size. So this is a question pertaining to the sampling distribution of all sample means. All right, which was chapter 10, this particular part of the question. How we learned in that chapter when we were talking about the sample distribution of the sampling distribution of the sample means, we said that the mean of all the sample means is equal to the population mean, irrespective of what the sample size is. The sample size does not have any effect on the mean of all the sample means. All right, on the mean of all, it does not have no effect. And in notation form, that means mu sub x bar, which reads as the mean of all the sample means, is equal to the population mean irrespective of the sample size. What about the standard deviation? Does the sample size have an effect on the sample standard deviation? Yes. The sample size does not have an effect on the sample means or the means of all the sample means, but it does have an effect on the standard deviation of all the sample means. So the sample size n does have an effect on the standard deviation of sample means. Greater the sample size, lesser the standard deviation. That means it's inversely proportional. As the sample size increases, the standard deviation gets smaller and smaller. All right? All right, so part C is a question on hypothesis testing, all right, and the error types that we learned about. It says, suppose that in a hypothesis test, the null hypothesis is in fact true. Is it possible to make a type 1 error explain? Right? So what is type 1 error? A type 1 error occurs. Now, in type 1 error, if you watched my lecture videos, we have explained there that in a type 1 error, the true null hypothesis ends up being rejected. That's an error. All right. And if you remember that analogy I gave of a court trial situation where the null hypothesis can be compared to the defendant, and the alternate hypothesis is like the prosecutor. All right. The null hypothesis is always assumed innocent as a defendant in a court trial situation. It's always assumed innocent. And when we end up rejecting or declaring an innocent defendant guilty and reject it, then it's an error. It's an error, and it's a type 1 error. And there in that lecture I had said, think about this I as innocent. All right? Just as a mnemonic to help you remember, think about this I to be innocent. All right? So when null hypothesis is innocent and rejecting, we end up rejecting a true null hypothesis. True null hypothesis causes a type 1 error. So the question here is asking, is it possible to make a type 1 error explain? Yes. If a true null hypothesis is rejected, a type 1 error occurs. So when the null hypothesis is true, the only error you can make is a type 1 error. Type 2 error, on the other hand, because the next part is asking about the type 2 error. Type 2 error is not rejecting a false null hypothesis. A false null hypothesis. So in other words, in a type 2 error, the null hypothesis is actually false, is actually guilty, but we don't end up rejecting it. We don't declare it guilty. All right, that causes a type 2 error. So however, when the null hypothesis is true, there's no way we can commit a type 2 error. No, type 2 error is caused only when the null hypothesis is false. In order to commit a type 2 error, the null hypothesis must be a false. All right. If the null hypothesis is true, then the only error we can commit is a type 1 error. The next part of the question says, suppose the null hypothesis is in fact false. If it's false, the only error that we can commit is a type 2 error. Is it possible to make a type 1 error if the null hypothesis is in fact false? No way. No, type 1 error occurs when the null hypothesis is true. Is it possible to make a type 2 error? Explain, yes. When we fail to reject a null hypothesis when it is false, a type 2 error is caused. So you have to support, for these questions, you have to support your answer with an explanation. You have to put in an explanation. If you just write no and yes, you don't get any points because you might as well be guessing it. It's not an indication that you have understood the logic behind the answer, behind whatever you have answered. All right, so make sure you follow up your answer with an explanation, and the question will say explain, so you have to explain anyway. Part E says a couple plans to go on a rock climbing trip, but they are nervous about the safety of their equipment. Use the following hypothesis to answer the questions below. The null hypothesis is stating the rock climbing equipment is safe, and the alternate hypothesis is claiming the rock climbing equipment is not safe. Describe a type 1 error in this situation. What are the ramifications? What are the implications is what it means. All right. Now, how would we describe a type 1 error in context of this question? In a type 1 error, the null hypothesis is true. What is the null hypothesis here? It's saying the rock climbing equipment is safe. And by a type 1 error, that means this is correct. This is true. All right. So you have to write it like this. The rock climbing equipment is safe. It's safe, but the test decides it is not. Somebody who did the test probably made an error and they think that it is not safe enough. All right. Ramification is that they missed their rock climbing trip due to faulty equipment, even though equipment is fine. That's the implication. All right. They don't use the that particular rock climbing equipment, even though it is safe. So perhaps they couldn't go to the to the rock climbing event, or they went and purchased another one which they thought is safe, and so on. You can just make up the ramification in this context. Part 2 says describe a type 2 error in this question. What are the ramifications? So in a type 2 error, the the null hypothesis is false. That means it is not safe. So this is dangerous. The rock climbing equipment is not safe, but the test decides it is safe. All right, that's dangerous, correct? So somebody is using an equipment which is really not safe. All right, ramification is that they use faulty equipment to climb, making it hazardous and unsafe. Okay, so this is how you should be answering these questions. You will get a similar question in the test. Okay. Part F says each score in a random sampling distribution of the mean represents what? A single individual, a random data point, a sample mean, a standard score. Whenever we talk about the sampling distribution of the mean, so sampling distribution of the implied word here is sample mean. We refer to a sample mean. Sampling distribution refers to a sample mean. It's not a random data point. It's not a single individual observation. It's not a standard z-score. It refers to a sample means. That means how different x bar values are distributed. X bar meaning sample mean values. Again, this is something that we discussed in length in our chapter 10 lecture, sampling distribution of the sample means. All right, that's a question related to that chapter. All right, so I think that completes the first question. We are next going to go to the second one, which is some problems on sampling distribution of the sample means. All right. Let's look at this question here. It says a variable has a mean of 266 and a standard deviation of 16. 10 observations of this variable have a mean of 262.1 and a sample standard deviation of 20.4. Determine the observed value of the standardized version of x bar which is the sample mean, and the studentized version of X bar. So the first sentence in this question tells us what the population mean and the population standard deviations are. Okay, so the mu, which is the population mean, is 266. I've written it out here. And the standard deviation, population standard deviation, is 60. Now we go on to what the sample mean is. 10 observations of this variable have a mean of 262.1 and a sample standard deviation of 20.4. So from the population, if we get a sample, all right, then 10 observations of this particular variable, they have a sample mean. So whenever we are drawing a sample from the population, then and calculating its mean, then that's the sample mean represented by X bar. So that's why I have X bar equals 262. Actually, I don't know where that 2.1 came from. So what I'm going to do is I'm going to get rid of it. All right, doesn't make sense. It should be 262. All right. So they have a mean of 262 and a sample standard deviation of 20.4. So just change that 0.1 to just 262. All right. Determine the observed value. So standardized version means the Z value. All right. So the Z formula that you're going to use is X bar minus mu. However, because we are working with sample means here, it has to be X bar minus mu over sigma divided by square root over n. We have to factor in the sample size. And what's our sample size here? N equals 10. All right, so we have somewhere here n equals 10. And we can, please do not use the Z formula without factoring in the sample size in the formula. Whenever our observations refer to X bar instead of individual values of a population, we have to use this particular formula, X bar minus mu over sigma divided by square root over n. And then make sure you're plugging in the values correctly. And this whole calculation comes to a Z value of negative 0.792. The studentized version of X bar is, of course, the T distribution. So it's going to be T equals X bar minus mu. Nothing changes in the numerator. It's only that the sigma is now being replaced by S because we do not know, we are not given, whenever we use the T distribution, we are not given the population standard deviation. So we have to use the S value or the sample standard deviation, which is 20.4. So again, 262 minus 266 divided by 20.4 over square root over 10, which gives us a T value of negative 0.62. All right, so that's how you are going to answer this question. What would be our DF for this particular T value, right? Again, DF for one population mean is goes with the formula n minus 1. So DF equals n minus 1. In this case, our DF would be 10 minus 1 equals 9. All right. But for this particular question, we don't need to mention the DF. However, later on, when you're finding confidence intervals when you're performing hypothesis tests, you will need to specify DFs. Okay. All right. So that answers question 2. Oh, well, it's not quite question 2 in your review sheet. This is a different review sheet that I'm using, but the question is the same. All right. So just go by the question, not by its number. Now, the next question is, as reported by Runner's World magazine, the times of the finishers in the New York City 10-kilometer run are normally distributed with a mean of 61 minutes and a standard deviation of 9 minutes. For the finishing time, find the sampling distribution of the sample mean for samples of size 4. Interpret your answer in terms of the distribution of all possible sample means. This is a problem that I have, I've already posted video solutions. It was a question on your worksheet on this topic. All right, so it was the exact same problem. So I don't want to spend too much time. I'm hoping you already went through it previously when you were studying the chapter. But I'll display the answer and briefly go over it here. All right. So find the to describe the sampling distribution, you need 3 pieces of information. One, you have to describe the distribution, and in most cases it will be normal distribution. You also have to state the mean and the standard deviation. Any distribution has to be accompanied by stating the mean and the standard deviation because the distribution is with respect to those 2 parameters. So the way I've written out the answer is, as the runner's times are normally distributed. It's normally distributed. How do I know that? Because it's given in the question. It says here, are normally distributed. So that's how I know it. So as the runner's times are normally distributed, the sampling distribution for means of sample size of 4, all right, here, you see over here, it says they want to know the sampling distribution for a particular sample size. So the sampling distribution is normally distributed for means of sample size 4, will also be normally distributed and will have a mean, that is the mean of all the sample means, will be equal to the population mean given to us for this question, which is 61 minutes, and the standard deviation, or written as sigma sub x bar. It goes with this formula for sampling distribution of sample mean. So sigma divided by square root over n. So 9 divided by square root over 4 is 4.5 minutes. Okay. Repeat the same thing for size 9. So again, the mean of all the sample means doesn't change with sample size. All right, regardless of the sample size, mean always stays the same. So it's going to say 61 minutes. However, the standard deviation is affected by the size. So sigma divided by square root over n. So 9 divided by square root over 9 is 9 divided by 3. So 3 minutes. So write it as a sentence. The distribution of all sample means will be normally distributed with a mean of 61 minutes and standard deviation of 3 minutes. All right. And then this part of the question says, obtain the percentage of all samples of 4 finishers that have mean finishing times within 5 minutes of the population mean finishing time of 61 minutes. Interpret your answer in terms of sampling error, show all work, and draw a clearly labeled diagram, and so on. All right, so they are looking for the percentage. So our final answer must be in terms of percentage. And whenever they ask for percentage, it should immediately tell us we need to know the area under the curve. All right, and it says for 4 finishers that have mean finishing times within 5 minutes of the population mean. So what was the population mean? The population mean was 61. So within 5 minutes means plus minus 5. All right, within 60, if 61 is here in the center, then within 5 minutes to the left, 5 minutes to the right. All right. So our x bar sub 1 and x bar sub 2 are going to be plus minus 561 plus minus 5 to give us 56 and 66 minutes. And we have to find the area between these two sample mean values, x bar values. All right, so one is 56, one is 66. So z sub 2, I always suggest, I will always recommend to first calculate the greater, the value which will lead to a greater, higher z value. So again, this is the formula we are using. There should be a sigma over square root over n in the formula because we are working with samples here, not population. So 66 is this value here, 66 minus population mean is 61 divided by 9 over square root over 4 should give us a z value of 1.11 and z sub 1 value corresponding to 56 should give us a value of negative 1.11. Find your area from the table, subtract it, and we get a value of 0.7330. Write it out as a sentence, your final answer as a sentence, and make sure you give the percentage form because that's what the question is asking. 73.30% of runners finished within 5 minutes of the mean 61 minutes. All right. And the next part says repeat the same for size 9, for a sample size of 9. Again, same diagram here, but our standard deviation will have to be divided by square root over n in this case, right? Because 9, the standard deviation will be affected by the size, sample size. So our first z value corresponding to 66 is 1.67. The other z value corresponding to 56 is negative 1.67. Find the areas from the table and we come up with a value of 0.9050, which translates to 90.50% of runners finished within 5 minutes of the mean of 61 minutes. All right, so these are the answers for this particular question on New York Marathon, New York City 10K run. Okay. We'll now go over this problem, which is an application-based problem on the sampling distribution of sampling mean. So this is again a problem where you will have to find the areas. So, but let's read through this word problem here. It says the recommended adequate intake RAI of calcium for all adults is 1000 milligrams per day. If adults with incomes below the poverty level have a mean calcium intake equal to the RAI, what percentage of all samples of 18 such adults have mean calcium intakes of at most 947.4 milligrams? Assume that the population standard deviation sigma is 188 milligrams. State any assumptions you're making in solving the problems, show all work, and draw a clearly labeled diagram representing the region of interest of the percentage. So this problem says or asks us to find the percentage. All right, so it says here, what percentage of all samples? So samples, this word itself now tells us that we are dealing with sample means. All right, so I'm going to extract the main data that we need to solve this problem. So percentage tells us that we are looking for area. Once we find the area under the curve, we can just translate that into percentage. by multiplying it by 100. So RAI, the recommended adequate intake, represents the mean because that is the accepted RAI for all adults, and that's 1000 milligrams. So mu equals 1000 milligrams. What is the sample mean? All right, so the sample mean that we are talking about of all samples of 18 such adults have mean calcium intakes of, at most, well, for the time being we can ignore at most, but 947.4 is the mean for 18 adults, for a sample of 18 adults. So X bar is 947.4. Extract the data and write it up front here, all right? Sigma, population standard deviation, is 188. N is this 18, all right? And what are we looking for? At most. Now we can look at this phrase at most. At most means less or equal to 947.4 milligrams. So they're asking us what percentage of intakes is at most 947.4. That means 947.4 is the highest value. It could be values less than that, therefore less or equal to 947.4. Start with a diagram again, all right? So in the diagram, we show that the mean intake is 1000 and our sample mean X bar is 947.4, and then it's less or equal to, therefore we extended a line from wherever 947.4 may be located. We know it'll be located to the left because it's less than 1000, right, where the center point is. And because it's less or equal to, our region of interest is the left-hand side. All right, so draw your diagram. It'll help you to move forward. All right, so we have to find the Z value. We are looking for the area of this region of interest, but we cannot find the area unless we know the Z value, the corresponding Z value. And we use the formula X bar minus mu divided by sigma over square root over n. All right, that's the formula we have to use because we are dealing with samples here, not population, but samples. So plug in the values correctly. If you have listed them up here, it's easy to pick them up and plug into the correct variables. X bar 947.4 minus mu is 1000 divided by sigma is 188, right? It goes here and divided by square root over 18. Again, this sign is division, not multiplication. I see sometimes students end up multiplying. Please, it's division, 1 sigma divided by square root over n. And when we do the calculation, again, show all the steps. When we do our calculation, we have a Z value of negative 1.19, right? Now find the area corresponding to negative 1.19. So the area from the table, please look it up. It's 0.1170, 0.1170, all right? So that gives us the area to the left of the Z value of negative 1.19. And once we have it, you just have to convert that to percentage and write out your answer. All right, so the interpretation of the percentage in context of the question is 0.1170 converts to 11.70% of all samples of size 18 of adults with incomes below the poverty level will have a mean calcium intake of at most 947.4 milligrams. All right. So this is how you're going to solve a problem like this. All right. All right. So we'll now go on to some problems which are related to actual inferential statistics. And then I'll put it in the next part of the solutions. All right.